Refrigerators are devices that are able to transfer heat from a low temperature reservoir to a high temperature reservoir, and they require work into our system to do such. Now, refrigerators didn't come about until refrigerants were made. Refrigerants allow the transfer of heat from a low temperature reservoir to a high temperature reservoir based upon phase change that occurs at low temperatures. Thus, refrigerators do not violate the laws of heat transfer that we have previously defined in this course. We've previously said that heat has to transfer from a high temperature to a low temperature reservoir, and that the reverse is not possible. Now we note that we have to put work into the system to circulate our refrigerant such that it is able to transfer heat from a low temperature reservoir to a high temperature reservoir. Now, this phase change process occurs within the evaporator and condenser. The evaporator are the coils inside your refrigerator. Refrigerant comes in as a saturated liquid or with low quality, and it begins to change phase as it picks up heat from the refrigerated space. Once it has reached a saturated vapor state, it is then run through a compressor, and then this heat is rejected from the condenser to the high temperature reservoir, i.e. behind the refrigerator. Now, this requires work into our system. Our work in is defined as QH less QL. Now, to quantify the performance of a refrigerator, we are going to define the coefficient of performance, denoted by the variable beta. Beta is equal to QL per our work in. Note, when we define beta, we're interested in the quantity of heat we are removing from our low temperature reservoir. Since work in was defined as QH plus QL, beta can be represented as QL per the quantity QH minus QL, or 1 per the quantity QH per QL minus unity. Now, let's consider an example where a refrigerator removes 8,000 kilojoule of hour of heat from the interior of an insulated space, while we have to provide 3,200 kilojoule per hour of electrical power. And we want to determine the coefficient of performance of this particular device. To do such, we'll use our equation that we defined. Beta is equal to QL per our work in. Our heat removed is 8,000 kilojoule per hour, and our work into our system is 3,200 kilojoule per hour. Thus, our coefficient of performance is 2.5. Lastly, we have to talk about heat pumps. A heat pump is a refrigerator, i.e. an air conditioner, that is run in reverse. An example of this is Fujitsu or Mitsubishi split units. Now, heat pumps are like a refrigerator in that we are taking heat from a low temperature reservoir. This is typically outside your house, and then we are transferring it to a high temperature reservoir, i.e. the warm space inside your house. Now, this also requires phase change of your refrigerant to happen. When we analyze a heat pump, we are interested in how much heat is delivered to our high temperature reservoir per our input work. Now, the coefficient of performance of a heat pump is denoted as beta prime. Beta prime is equal to the heat supplied to the high temperature reservoir, i.e. the interior space of your house, per your work input. And our work input is unchanged. Our work input is QH plus QL. Therefore, beta prime is QH per the quantity QH minus QL, or 1 per the quantity 1 minus QL per QH.